Hello, Mr. Mailer here, your online math teacher. Welcome to my channel. Today we're going to be continuing my video series on confidence intervals, and in particular asking the question, why t-distributions? So when you talk about using one sample t-intervals to estimate your population mean, why are we using a t-distribution and not a standard normal distribution? So your z-scores, like you did when you looked at proportions. So we want to investigate that a little bit more in this video today. So if you find this video helpful, consider smashing the like button, subscribing, and let's go. So this is the same context that I'm using in my video where I go over an example of doing one of these problems. So this isn't me going through the problem, you're just talking about one aspect of it. But you have a student at a large university, they want to study GPA of full-time enrolled students. They take a simple random sample of 72 full-time enrolled students at the school and finds that in their sample there is a GPA of 2.9 with a standard deviation of 0.15. So that's what this student gets from their simple random sample. Now, to do this problem, they want to construct a 95% confidence interval to try to give some plausible values for the actual true population mean GPA. And they're using their sample statistics, so this point estimate and the sample standard deviation. So we want to know, why are we using a t-interval and not a z-interval here? So that's really what this video is about. So it really boils down to the conditions in a sense. So if we go back to the conditions you need to check, you have your normality condition that says we can generalize the population. That's fine. The 10% condition, yep, we can take our simple random samples and we can use our standard deviation formula for sampling distributions for sample means. So that's good. And hey, our sample size is big enough and standard deviation is finite, so we can apply the central limit theorem. Hey, this is all good. This should tell us we're normal, right? And the key is yes, your sampling distribution is going to be normal. So the sampling distribution of sample means is normal. But the issue is you've approximated a few too many things. So when we look at this problem, one thing we've approximated is the mean of our sampling distribution. So we are using our point estimate to approximate the mean of the sampling distribution for sample means. That's fine. That's no different than when you were estimating the mean of your sampling distribution for proportions with your point estimate there. But the issue comes in with standard deviation. The standard deviation formula for your sampling distributions for sample means requires you to know the standard deviation of your population of interest. You didn't have that when you were looking at proportions. You still just use that same old sample proportion. So we have to approximate the standard deviation of our sampling distribution using the standard deviation of our sample. And that's also one of the reasons why we're calling it the standard error instead. So we had to use two statistics to approximate stuff here. And the issue is approximating the population standard deviation with our sample standard deviation. When we do that, we're interested in inserting a lot more variability. And if we were to just go ahead and use a standard normal table and estimate with z-score, so use z as our critical value, when we go to ask for a 95% confidence interval, we could do all your computations fine, but you'd actually have a confidence level lower than 95%. So what that would mean is that if you were to take many samples with this process and keep constructing more and more of these confidence intervals, you would find that less than 95% of the time your interval would capture the true population mean. So it would be less confident than what we think it should be. So that is really the issue with when we're estimating our population standard deviation using our sample standard deviation. And the t-distribution is what helps take into account our correcting the fact that we're using this as an estimate. So we didn't have this issue with proportions because you didn't have to have a standard deviation, you had to estimate there. So what's the difference between a t-distribution and a normal distribution? Well, your t-distributions kind of are just shorter, fatter versions of your normal distribution. So you can think of there's more area weighted in the tails for a t-distribution than a normal distribution. So you can kind of see here the lower, what I call the degrees of freedom, which relates to our sample size, the shorter and fatter this curve is. The higher the degrees of freedom, the closer and closer our t-distributions get to our normal distribution. So this dotted line. So the way it works is your degrees of freedom is going to be one less than your sample size in these problems. So the higher the degrees of freedom, the larger the sample size, the more sure you are of your intervals. It's going to make your t-distributions get closer and closer to being approximately normal themselves. So if you have a really, really large sample size, you actually could get away pretty good with using your standard normal table and your z-scores. But especially for smaller sample sizes with low or degrees of freedom, you really need to make sure you use a t-distribution. Otherwise, your estimates will be pretty far off. Your confidence level won't be what you claim it is. So I hope this video gave you a little bit more insight. It's not the most technical video in the world, but that's fine. This is intuitively what's the difference. So if you found this video helpful, consider smashing the like button, subscribing, and have an awesome day.